Adam for letting me chair this session. Thank you, Renata, for tolerating it. I give a very brief informal introduction for this informal atmosphere. We're going to hear Renata talk about some dirty business.
Well, good morning, everybody. I would first like to thank organizers for inviting me, also giving a chance to give a talk. So today I'm going to talk about the graph partition problem. My title is quick and dirty versus strong and long. So if you if you try to figure out actually what it is, you will think that the title is really not informative, but the title is actually quite informative. So let me say a brief outline of my following talk. So I'm going to talk about the graph partition problem, and then I'm going to look graph partition problem for the two different ways of constructing the relaxations. So I'm going to look at the matrix lifting and vector lifting relaxations. So it's globally thought that matrix lifting produce weaker bounds than vector lifting. So what I'm trying to show you today actually whether it is always the case and when it's not the case. So what I'm going to do, because I say I'm going to do quick and dirty, I'm going to try now to simplify the matrix lifting approach, which is already much more simple than a vector lifting approach. And then I'm going to try to complicate the vector lifting approach. Okay, and then finally I'm going to bring some conclusion and tell you actually how those two things then relate. Okay, so let's start quite easy. So I'm going to first introduce a graph partition problem. So suppose now we have an undirected graph. Through the whole my talk, I will say about graph system G with vertex at V and edge at E. I will suppose I have n vertices. Okay, so what is a K partition problem? It's a rather simple problem to describe. You want to find a partition of the vertex set in a K subsets of the given sizes. So the sizes are something which is given to me, and I want to minimize the total weight of the edges joining all those sets. Okay, what we probably all know, if sizes of all these mi's are equal, then we have a graph equipartition problem, and when k is equal to 2, we talk about the graph bisection problem. Okay, so how do we model the problem? Now we have A is adjacency matrix of the graph, and we have a given M, so we want to make a graph partition with those sizes, partition the vertices in the size of vector M. And we define the matrix X, which is going to tell you X of ij is equal to 1 if node I is in a set Sj and 0 otherwise. So what does it actually mean? This matrix X is of size Rn times k. And actually each column in this vector X is going to be a vector which is telling you which of the vertices are in a given set. So it's going to be a heuristic vector of your set. Okay, so now what I'm going to do, I'm going to define the set Pk, and this is going to consist of all those matrices, and clear in this matrix some of the each row is equal to 1, and some of the each column is equal exactly to the M, which are the given sizes of the problem. Okay, so now comes the easy part. If you realize actually that if you multiply X transpose AX, trace of that, you get the weight of edges between the sets. And now in order to get what is actually the graph partition, you only need to subtract all weights of the edges in the whole matrix minus this guy here, and then you get what is the size of your cut which you want to minimize. Okay, so now we arrive to the trace formulation. 1/2 because it's a symmetric matrix, and we want to minimize over this set. And it's known it's a NP-hard problem, and it also has lots of applications. So therefore, it's quite interesting to study this problem. Okay, so let's talk now about so this was the first part that probably most of you know. So now let's talk about something that might be new for some of you. So suppose now I'm going to talk about the matrix lifting for the graph partition. Okay, so now I have my standard assumption. I have this size of all sets Si is Mi. They all sum up to the number of the vertices, and I want to linearize the objective function. So I'm linearizing objective function. It's very easy. I put this X transpose to the other side, and now I instead of X transpose, I say, okay, this is going to be my matrix Y. So this is quite standard approach. what is actually interesting to show that if y is a convex hull of all these y's for which exists the x in the previous set small pk, then you have actually k times y minus matrix of all ones is positive semi-definite. Right, so what you could also see, it's easy that you can impose in the relaxation that y is positive semi-definite, but if you know that this is also valid, then you actually have a stronger constraint. Okay, so now what do you get? You want to minimize the objective function. You know that diagonal y should all be ones, and then you know that the sum of the all elements in the y should be equal to this guy here. We have positive semi-definite constraint and non-negativity constraint. What is actually interesting, when k is equal to 2, then we don't need those non-negativity constraints. So actually what is interesting, this simple relaxation didn't appear before. Actually it was known for the equipartition from the bisection, but was not known for general M. Okay, so let's see now, make a connection with what we know the other relaxation of the equipartition, of the graph partition. So now if we have an equipartition problem where sizes of the all sets are equal, then it's well-known relaxation with Franz and Karish, and actually what we can show that those two relaxations are equivalent. So in a sense we can do both of them to obtain the same bound. This is not quite surprising result. Now if we take a look at what happens, we have a bisection, so the k is equal to 2, then again is a quite known relaxation about Karish, Rendel, and Clausen. And they, so this relaxation, if you see, also does not have non-negativity constraints, because non-negativity constraints are here also redundant, so we don't need them. And again, what it's not hard to show, that the relaxation which I introduced before is actually equivalent to this one.
So you lose the sizes of the individual sets in these relaxations.
Yes, yes, yes. But what will turn out is actually not too bad. I mean.
So the matrix Y kind of records for every pair of nodes whether they are in the same set.
Yes. If I and j in the same set, then position ij is 1. So therefore, then when we multiply with A, we get actually what is the size of the or the weights inside of each set. Okay. So.
Sorry, you mentioned that the non-negativity constraint is redundant.
Yes.
Why from this?
From here.
Can you derive that constraint is redundant?
Yeah, I can actually probably try to derive you from my relaxation from this one. So you get here, when you write this down, this part, then you actually set it, then you actually automatically get that they are non-negative, but maybe I can try to do it afterwards, right? It's really not hard to show this. But for the equipartition, you really did need that constraint, yeah? Okay. So where do we come? So we come to the improvement. So as you said, you don't have many information here, so you would expect that this relaxation is rather weak. And so then you somehow try to improve. So the question is how you can improve. You can improve by adding some extra constraints. So the first type of the constraints which you can add are triangular constraints. So what does this guy say? If you have a triple ijk, and then this constraint says that if ij are in one set and ik are in one set, then also should be jk in the same set. Right? So this is just pushing that all three of them are in the same set. And you have, of course, and choose 3 of those type of the constraints. And then you have an independent set type of the constraints, independent set type of constraints. And what does this guy say here? This guy said that there is no independent set of size k plus 1 that can appear in your relaxation. This is also quite easy to see. So if you have I, j, and k, and if I and j are not in the same set, then ij would be 0. Would be 0, then ik would be 0. and then also follows that jk has to be actually 1. Yeah. So this type of the constraints are rather strong, but they appear n choose k plus 1 of those. So what you can try to do, you can try to formulate the cutting plane approach and then try to add all of those constraints to the addition to the original relaxation. And what actually shows, I tested about 1,000 different graphs, and it turns that if you keep adding the triangle inequalities, then you always end up with a stronger bound. Yeah, and if you try to add only independent set inequalities, then the bound is always weaker than adding only triangle inequalities inequalities. If you try to add them both, then you end up with many constraints, and actually it's not worth adding both of them because the bound does not improve too much. And also independent set inequalities seems to be also most of the time, most of them anyway satisfied inside of relaxation when you solve the matrix lifting relaxation. So it really, if you want to start testing this, don't. Just use the triangle inequalities. Okay. So I have a small info further. So for the graphs with 100 vertices, the best known vector lifting relaxation is the one that I still didn't present you, but you will see in half an hour approximately. And this is actually hopeless. If you want to solve this relaxation, you end up with 27 hours computational time, which is not really interesting for anybody. If you add the first relaxation plus the triangle and independent set inequalities, then after 3 hours you get some reasonable good bound. But again, this is not what you want. It's still expensive. So if you add only triangle inequalities, you can get about between 1 hour. So I'm talking about graphs of 100 vertices, right? They are already large graphs for us. And if you just solve the basic one, you can get the solution in 12 minutes.
So you talk about the B-partition here? Or?
No, I talk about any partition because for me it doesn't matter because my relaxation does not depend on the size. It's always size n times n. It doesn't matter on the relaxation of the partition. Okay, so now we are quite happy. We have a relaxation that was not known till now, but so you can solve it somehow reasonable. But still, for you, most of you will think, okay, 12 minutes for size graph of size 100, can that be better actually? So questions, can we do it more efficient? And the answer is, of course, yes. Otherwise, I would not pose this question. So I'm going to show you now two different simplifications of this relaxation. The first one is related if I'm trying to simplify the relaxation for some graphs which has a large symmetry. Right? And the second one will be what happens when the graph does not have any symmetry, when I don't care of the structure of the graph. So when I say highly symmetric graphs, I mean that automorphism group of that graph is quite large. Yeah. So what do I suppose now? That A belongs to matrix star algebra, which is spanned by those matrices. And so I decided today not to talk about algebraic symmetry and in defining all these necessary things for this, but I am really willing to talk with anybody that wish after the seminar about matrix star algebra. But for you, it's only important to know that it's actually just a subspace. This is also closed under the multiplication and transposition or conjugation, depending if you have the R or the N. So so now I suppose the A belongs to matrix star algebra, and I have those matrices A1 to AR. I can generally compute them. These are actually nothing else but just the orbitals on the pair of indices I and J's. And what I also suppose that R is larger than n squared divided by 2. Otherwise, it has no much smaller than n squared divided by 2. Otherwise, it would have no sense to look at this approach, right? Okay. So if the SDP relaxation has it could be shown if SDP relaxation has an optimal solution, then also has an optimal solution in the matrix star algebra. And this is actually you can take a look at one of the Dimas paper. It's also in a handbook of I think it's also this type of the proof in a handbook of Miguel and Nasser. But you can also take a look at this paper here. So what actually then we can assume that this Y is nothing else but the linear combination of my matrices, which I call the basic matrices, So it's just a linear combination. If R is small, I have only R variables, and if R is small, I should be very happy. Okay, so if now I'm very happy that I can actually plug this into my relaxation, and then I obtain this formulation of the original relaxation. So what I know here, I know A, and everything what is blue is actually essentially what I know. So I can easily compute it, and I end up with a small SDP problem, which is only R variables are supposed to be quite small, and I have one SDP constraint. Yeah, so it's just simply plugging in. So in a sense, if I have a highly symmetric graph, then I can solve this less than seconds. For these graphs of 100, I get it in less than second, just a solution. Okay, but this is not something very spectacular, especially for you that you don't know how to obtain those basic matrices. But I can give you a couple of examples where I can actually make it closer to you what we do. So if I suppose now I have a strongly regular graph. Yeah. So what is a strongly regular graph? For the strongly regular graphs, I know that adjacency matrix is exactly two distinct eigenvalues. One of them is non-negative, and one of them is negative.
There should be one more.
Yeah, but associated with the eigenvectors orthogonal to vector of all ones.
Okay.
Yeah. So I don't count the one that is associated with the eigenvector of all ones. Of course, there is the third one, which is equal then to 0. No, it does not have to be equal to 0, is equal to the degree. Okay. So now I know that how it looks, adjacency matrix of that graph, and I know that it's completely characterized by the values n, which is size of the graph. Kappa is the valency of the graph, and these two eigenvalues R and S. Yeah.
Well, completely characterized is misleading. There could be many non-isomorphic graphs with the same parameters.
Yeah, up to the. Yeah. Okay.
It's not
Yeah,
up to.
okay.
It's just they can be different. So.
Okay. So they are characterized by those values.
Characterized in the sense that the eigenvalues can be computed.
Yeah. Okay. But but let's see what actually we can do. So if we have those parameters, this only, and I suppose now that I have a given vector of the length of the subset that I'm interested in, then the SDP bound for the minimum K partition is nothing else than the maximum of those two expressions. So it means actually I can just get it just plugging in those two values.
So the SDP is completely characterized by this parameter.
Yeah.
Something is
Yeah.
completely characterized.
Yeah, the SDP bound is for the minimum K partition is exactly those two, and similarly, if I look for the maximum K partition, I also get only this expression, and this is then very cheap to compute, right? This is no computational time
But
required.
is the partition problem known to be NP hard on strongly regular graphs?
Yeah, that's what I don't know, but I would doubt, right?
No,
Do you know, Dima?
No, I don't.
No? Okay. Yeah, that's actually good to take a look, but I doubt, right?
I doubt.
I doubt. Okay. Okay, so this is quite a beautiful expression. I find it very nice. But this is a sort of extension of our previous results with Dima, Etienne, and Christian.
So did you have to solve a small linear program?
Yes. So actually, that's actually a good question. So what do I do here? Yeah, I should come back to this part. So what do I do here? So now I know that this AI, AR, I have only 3 of them. Is identity matrix, adjacency matrix, and then the rest. So I put all these things inside, and then I end up with R is equal to 3. And then I have this expression here, which is my SDP, and then I know I can simultaneously diagonalize them. So then I simultaneously diagonal this part, and I end up with a system of 3 linear equations, and then I just take a look what happens there.
So,
Yeah.
so whenever this algebra is commutative, you can.
Yes.
You have a linear program.
Yes.
That one,
Yes. Yes. So this is actually on one of the next slides. So this is quite nice. I find it quite interesting result, and there are many groups of the graph, classes of the graphs where I can actually do it, right? that have some interest in the graph theory. Okay, but so what is interesting, exactly what Dima said, is that for Johnson and Kneser graphs, for instance, this reduces to a linear programming problem, right? Again, it reduces to a linear programming problem for which it's a little bit harder than for the strong regular graphs to get this exact formulation, but if I work a little bit harder, I can get also for those group of the graphs, because Johnson and Kneser graphs can also be simultaneously diagonalized, right? Okay, so let's go now to, which is something maybe more interesting, because you can say, okay, I have lots of graphs, they have lots of symmetry, but I mean, who cares? Sometimes you want to get a bound for the graphs which don't have so much symmetry, right? So what I'm going to do now, I'm going to show you some simplification for a not special graph. So it means I want to show you when graph has no symmetry, at least not the one that I know. Okay, so I want to get again a closed form expression for the graph partition problem for any graph, yeah, without the symmetry, also for those with the symmetry, but anyone. So what I'm going to look now, I look the following. I define by L is going to be spanned by those matrices F0 to Fd. And this is what I'm going to call the Laplacian algebra, which is actually algebra. This is corresponding to the L, which is the Laplacian of the graph, right? So, but I have to tell you a little bit more about those F's. So F is of this form, where this UI's correspond to the distinct eigenvalues of lambda I. So what does it actually mean? It means that for every I, UI is going to have a columns that are going to be orthonormal basis for the eigenspace of lambda I. Yeah? So I can do it, and I know that actually they are basis of idempotence. So they have this nice structure. They all sum up to 1. I know that conjugate actually here could be transposed. And I know they are orthonormal, and what is also interesting for me, that I know that the trace of Fi is nothing else but the multiplicity of the ith eigenvalue of L. Yeah, so I have some nice basis for which I know a lot, and what is interesting that for actually that basis, Laplacian, for the Laplacian algebra, I can form it for any graph that I wish. Yeah? So it doesn't have to be some special graph. Okay, so now I want to simplify.
So it is a particular basis
Yeah.
in the algebra spanned by the powers of L, right?
Yes, yes, completely, exactly that. I mean, I can have the other different basis, but I want this one. Yeah. Sure. So, so now what
So they are only real numbers.
Yes, yes, yes.
So the Fi equals Fi star, that is the conjugate.
Yeah, I said it
That
could
is
be.
the transpose.
Yeah, I said it could be transposed.
Oh,
It was
sorry.
my type. I already mentioned it. I just noticed right now. Okay, so yeah, you're right, and it's even more simple. So if you forget about conjugates, right? Okay, so so what I want now, I had this my simple relaxation that I still want to simplify, but by using this Laplacian algebra. But I have some troubles if I exactly use the one that I defined at the beginning. So I need to relax some of the constraints. So I'm going to relax this constraint. I'm going to relax a diagonal of y is equal to vector of all ones. I'm going to say that trace of y is equal to n. I can do that, right? I get something weaker, but I can still do that. And I want to remove non-negativity constraints. This first part is going to be clear. Actually, why I want to remove this, because I can use the property that trace of Fi has the multiplicity of the ith eigenvalue of L. So that's why I want to relax this constraint to that one. Yeah. But now is the question why I need to remove the non-negativity constraints, because I have no guarantee that this basis of F0 to Fd are non-negative matrices. And what actually I had in a previous, when I would have a symmetry and then find a basis which is formed from the orbitals of the pairs of the indices, then I knew that my basis has 0 and 1s, and because I have a non-negativity constraint in original relaxation, I just only have to impose that this yi is a non-negative. But here I have no restriction like that, so therefore I cannot say that they are non-negative. So I decide.
I guess there will be examples when those Fi's cannot be non-negative, just because they are actually uniquely different.
Yeah. Yeah, so I just generalize, yeah. There is no probably not too much to say about this for people that know a lot about those things. Okay, so then I end up with this GPP closed, and this has this form, right? I remove non-negativities and I have this constraint. And now what I do what exactly I described 10 minutes ago. I just can say that I assume that all my yi's have this structure, right? They are just linear combination of those. And then I plug this y is equal to the sum of the yi fi's here. And then I work a little bit, not too hard. And then what actually ends up that I have the following, that for the given graph, any graph, and such that the sum of the weight sum up to n, then this GP closed bound for the minimum k partition is actually equal to this guy. So it means that if I want to find the minimum k partition for a given graph, then I only need to look at the second smallest eigenvalue, because the first one is 0, and then look at those guys here. And then if I want to look at the maximum, then similarly I look at the largest value and largest eigenvalue, and then get this expression here. Okay, so this is, I think it is quite cute result, because up to now it was not actually known that there exists such expression for the graph partition for any partition. What was known, there was when k is equal to 2 and k equals to 3, then those three guys actually had an expression which coincides with mine for k is equal to 2. And when k is equal to 3, the one that Franz has is a little bit stronger. So it means that we still have to take a look how we can improve this. So, but this is really ongoing right now, research.
How does the bound and relate with the other that you...
Yeah, this is the next slide. Okay, so the next slide I have chosen some graphs which Dima will probably say, okay, but these are nice graphs, right? I even removed one strongly regular one this morning. So I have a collection of the different graphs. So first I take a random graph, size 50, I do the bisection, and then I actually get that this GP closes for 31 values less than this one, so it's pretty bad, right? But it still gives you some information. So if you want to do, for instance, branching bound and you have to start with some root node, it's quite good way to go, right? Just for the random graphs. Then if I take a look at this dope graph, this is, I think, a distance regular graph. Again, bounds can be bad. If I take a design graph, I can get the same. So design graphs are coming for the designs, and I get actually the same values. And I take a grid graph, which is a grid graph of grid 10 times 10. Then I get a difference only for two values. So which actually means that the bound is for free, and it's not too bad, right? So you can use it. But what actually what we are currently looking, we are interested in actually how to improve that bound, right?
So what is in the third column of this table? What is K?
Third
one, this one.
Yeah,
I just choose
8.
any partition, yeah? So here is 8 partition, 9 partition, and here I just...
So some a partition in 8 parts? Or?
Yes, 8 partition, K partition, equi partition.
Okay.
8
Okay,
partition, K partition, huh? As they are all the same. So it's 8, yeah, and the other one is 10.
So your new bound, I'm just thinking, there's the part that depends on the graph, and then there's the part that's the sum I less than j,
Yes.
I and j, which is worst when the numbers are balanced.
Yeah.
But your other bound, where you have trace of something and you have summation mi squared, has the opposite behavior. I
Yeah.
think. So I think you can make the results go as you like.
Yeah, could be probably, yeah. Depends on the graph, depends on the partition and whatever you look, right? Yeah, I actually took a look at that, yeah. So the best is somehow not too large case to take so that they are closer
So
somehow, yeah.
Did you actually relax your Fi's to be just positive semi-definite?
No, I didn't relax them.
Rank or given rank?
No, I didn't do that.
I didn't do that.
But
So
actually this is maybe the
this-
way to go, right?
So what you presented there is not an SDP relaxation, it's some particular relaxation
Yeah.
that allows you to
To do that, and
do this. Okay.
so, yeah.
So this bound actually fully utilizes as multiplicities, this ranks of those Fi's.
Yes, yes, that's what I actually use. Therefore, I relax the original constraint, right? But I think this could be better. I think we can improve something over there. I think there could be some things could be added to the relaxation itself to improve it, which are actually redundant for the original one when I had vector of all ones. So it's just the name of the game. Okay. So my actually thing is what I'm going to do in the next few weeks or so. I want to really improve this guy here. Okay. I'm doing right now good on the time. It's half of the time now. So I said if my talk is going to first part going to be too long, then I will make a break. But I'm doing well. I will finish in 1 hour. Yeah? Okay. So what I actually want to show now, I want to do the vector lifting of the graph partition problem. So now I'm going to do the following. Again, I have the same problem, graph partition problem. I have M, which is a vector of, which gives me the size of the partitions which I want to use. And then again, as before, X is belonging to this PK. This PK is just my partition matrix, which tells me the sum of all elements in a row is equal to 1, which means every element belongs to one set, and the sizes of the subset has to be given, has to actually coincide with M. And now if you do the metric vector lifting relaxation, what you're supposed to do, now you take a vector Y, you vectorize your X, you plug in, stuck in column by column, each column of the matrix X, and then you obtain matrix Y, and then standard approach is just to relax the Y to be positive semi-definite. So now is Y, actually this Y here, size of this Y, it came K times N, where K is the size of the partition, and it means K is large, then this is very large, right? Okay, so what do you do now? You just rewrite your objective function, so it's this guy here, size K times K, and A is N, Kronecker probability is K times N. These guys here are telling you that every column in your vector X is orthogonal. So therefore I have all those zeros, and here I inherited the actual generalization of the constraints that I have the sum of the all rows is equal to 1 and sum of the all columns is equal to M. So this is here. And then I have my positive semi-definite constraint, and I also want to impose that they are all non-negative because I am dealing with the 0, 1 problem. And this actual relaxation is from Volkovich and Zhao. The only thing is that actually Volkovich and Zhao didn't include no negativities, but if you think of in 1999, it was absolutely amazing to solve such a SDP even without no negativities. So I guess this was the reason why they didn't include it. So therefore I call it Z, W, and N is just no negatives, which I add as well. Okay. I'm now going to show you some results. The first one is absolutely not surprising. And first one says let K is equal to 2, so it means now we have a bisection. And for the bisection, I know that this vector, I can prove that this vector lifting relaxation dominates the matrix lifting one. This is quite really to be expected. But the second one is the one that also surprised me. The second one says if you have an equipartition, so sizes of the all subsets are equal, then the SDP relaxation vector lifting one and this matrix lifting one are actually equivalent. So I didn't get it at the beginning because when I do numerical results I think that it's the same bounds, but I cannot test the other bound for the vector lifting for large K, and then so I was not sure what is happening, so it took me some time actually to prove that they are really equivalent. So it was like a long proof, but I think it's quite a nice result. So what else I can show, it's not written here, for K is equal to 3, also the vector lifting one is dominating the matrix lifting one, and I didn't go further, but I would expect that for any K larger than 3 this also happen, except for the equipartition, any size of the equipartition. Okay, so now let's take a look what my numerical results show. That this graph partition vector lifting one provides the best bound, but computations could be quite demanding, so I cannot get with that one for the graphs of size larger than 50, otherwise it has no sense. I made the partition of 3. And okay, so now I actually give you an example. For K is 3 and N is 100, the vector lifting one requires 27 hours, but the other one only 12 minutes. That's already I told you before. And what is also interesting, then if you take a look at the metrics and vector lifting one relaxation and you increase the k, then actually those bounds are getting very close. So for my test of graphs of when k is larger than 5, I always get the same bound. So maybe something there is happening, which is probably possible also to show. So it means if you have a partition where k is larger than 5, then just do the small relaxation and you're guaranteed to get one probably very close to the best bound. Okay, so the second part, I said I'm going to show you the more complicated relaxation. Then what I want to do, I want to improve this relaxation, so I want to strengthen that one. So you would think of, okay, but it sounds a little bit crazy. She wants to strengthen something which is already quite strong, and then if you strengthen means you add some extra constraints, it means it's going to be harder to solve. But actually this is precisely what I want to do. What I want to show you, I will demonstrate how to strengthen that relaxation for the min cut problem. Yeah? Min cut problem is a special case of the graph partition, and I will tell you a little bit more about that further. Before I talk about the min cut problem, I need to tell you why I need the min cut problem, because it's quite artificial problem. Okay, so I'm going to use the min cut problem.
Artificial in which sense?
Yeah, because you have two subsets for which you want to minimize the connection between them, and the rest you don't care. This is what I'm going to call the min cut. You split into 3 sets, and then you want to make a connection between 2 of them, and for the third one you don't care. Yeah, this is just a special case. So to talk, but I will come back to that actual relation with the bandwidth problem a little bit later. But now about the bandwidth problem, because I will need it for the min cut, let me introduce it to you. Okay, so what is the bandwidth problem in the graph? Is the following. Now again, you suppose you have a graph which is undirected, you have a vertex set and you have an edge set. Yeah? Okay, and now I define something which is called the labeling of the vertices. So what is my labeling of the vertices is going to be the bijection from the vertex set V into the set of 1 till n. Yeah? And now what I'm going to call the bandwidth on the labeling of phi is going to be this guy here, and this is going to the maximum of all differences for the all edges for my given phi. Yeah? So I just decide I have a one bijection, and then for that bijection I look at differences for the all edges, yeah? For the all adjacent vertices. Okay, and then I call the bandwidth of the graph is going to be the minimum of those maximum over all bandwidths of the labelings. Yeah, so it sounds quite strange what I want to do, but in other words, I want just to give numbers to the vertices and then look at the maximum distance between all possible combinations between all edges, and then I want this to go down, right, to be as small as possible. Okay, so again, this is my nice definition, but
Phi should be a permutation? Or?
Yeah, phi is a permutation, sure. Yeah. So again, this is the definition, but I guess the picture is worth more than any formula. Okay, now I suppose I have my cube, and now I gave the numbers to the vertices, and I have if you check, the maximum is 8 minus 1 is 7. Yeah, so this is going to be for this labeling, this is going to be my bandwidth of this labeling. And then now what I have here, I give a different numbers to my cube, and then if I take a look, then the maximum difference is 4. And now if you know anything about bandwidth, you know that this cannot get better than this 4. And if I put now in adjacency matrices both of those cubes, then for the first one it will look like that. So it means I will spread non-negative elements of ones all over around. And for the other one, I will actually try to stay as close as possible to the diagonal. And this is going to tell me my bandwidth is 1 minus 5 is going to be 4. So my bandwidth is 4. This is the optimal labeling for my graph. So and it's actually, yeah, so you want to stay as close as possible to the diagonal. And the problem is quite interesting for the computer scientists, so when they want to do some pre-processing or so, it works much better if you have such with a small bandwidth graphs. Okay, so now this is my bandwidth problem, but where I come now, I want to define the minimum cut, actually to draw the connection between minimum cut and the bandwidth. And this is the following one. So now I suppose I have 3 subsets. They are going to be S1, S2, and S3. And I give them the sizes M1 till M3. Yeah? So it is the same as in the graph partition problem, but my min cut problem is the following. I'm interested only to minimize the connections between sets S1 and S2. And for all partitions, and I give in advance what are my sizes, right? So I say it's rather artificial because I'm only interested in the connection between those 2 sets. Okay, so it's clear that this is a special case of the graph partition problem because my matrix of the partition X matrix, partition matrix is actually going to be the same. What I have different is just my objective function. So now let's take a look what is the relation from this problem to the bandwidth problem. So again, I go to my favorite hypercube and and I say let M1, M2, and M3 are going to be sizes 2, 3, 3. So 2, 3, 3, yeah? And now what I'm going to look whether there is a connection between set M1 and set M2. Yeah, I see there is a connection between those, and I know the following, then my bandwidth has to be larger than N3 plus 1. Yeah, this is clear. Yeah, so, and if I don't have a connection, so if this set would be here larger, then I could not conclude anything. So I have to reduce the M3 and then check whether there is any connection. So the problem is rather difficult. It sounds to be rather difficult because from the beginning I don't know the set of the sizes of M1, M2, and 3, right? So, and I have to not guess them, but I really have to resolve all the time to get whether there is any connection. But this, what I see here, this is rather simple observation, right? But what we actually can do, we can do a little bit better than this one. So we can say, so actually what I'm showing you now, this was first noticed by Polynomial and Redel and then later improved by Edwin and myself. So we actually took a look that there is a more involved the relation between those 2 sets than just M3 plus 1 to tell you there is a bound. Because if you see here could be also 1 and here could be also 1, right? So, but then you want to get the best from your bound. So it means if you have an optimal value for the min cut and then you have some relaxation of the problem, then actually you can conclude that your bandwidth of your problem is depending on N3 plus this expression here. But this expression here can sometimes help you a lot to get a better bound. Okay. So, so it's clear now from this expression, if I have a tighter bound for the minimum cut, then actually I'm going to get a better bound for the bandwidth problem, right? So it means I want to somehow to improve my relaxation of solving the min cut problem. Okay, so first one, because I introduced you for the previous, for the matrix lifting, I introduced you eigenvalue-based bounds, so they are quite sometimes useful to solve. So therefore, I'm also going to show you the eigenvalue-based bound for the min cut. This is from Helberg and France and Mohar. What I actually said that eigenvalue bound is given in this form. I'm not going to go into the details. Here again they take a look at the second smallest eigenvalue, the largest eigenvalue. And they get, this is actually the bound. And how do they get it? This is again the closed form of some minimization problem over this set. Right? And again, this is quite easy to compute, but not very strong. So what I suggest, we actually suggest the following. We suggest to solve the graph partition problem, the matrix lifting one, with the following objective function. Yeah, this is just objective function when I connect 2 sets, and then I have adjacency matrix over there. So the size of this one is 3 times n, where n is the number of the graphs, and 3 is because I have 3 partitions, but I don't care the third one. And what actually we can prove that this vector lifting one is stronger than the eigenvalue one, which is trivial to see, but it's not so easy to prove. But this is something what you might expect. Okay, but those bounds already know, but you want to do probably something better. So I want to strengthen this vector lifting and relaxation in the following way. There are different ways how to do it, but actually the way how I did it, I am going to describe here is the following. So I want to fix an edge and a non-edge in a graph with the adjacency matrix A. Yeah, I just want to fix. And I'm not telling I want to fix an edge, I want to fix edge or non-edge. Okay, but which one? Yeah, what do I have to do? I take a look at the action of the automorphism group on the pair of the vertices, right? So I take a look at my orbital, this guy here. Yeah, and then depending on the automorphism group, I will end up with the different orbitals. And what I claim that actually those orbitals represent the different kinds of pairs of vertices. I'm not talking here about the edges, because in the orbitals can be also included a different kind of the non-edges, okay? So that's clear. And what I assume, I have T of those. Yeah, T at this moment I don't care what is T, but for some nice graphs this T is rather small, and for the other graphs it's not, right? So, but I want, of course, to have a T rather small. Okay, so what we can prove the following. I can prove if G is an undirected graph with my adjacency matrix A, and I have T orbitals of edges and non-edges. Yeah, these are all classification of my connection between the different set of the vertices. And now I can fix, take RH1 and RH2 as an arbitrary pair of vertices. So I just take one pair of vertices in my orbital. Then I can actually show that my graph partitioning problem is actually equal to the minimum over the minimum for all these different T's, so I do the following. Let's do it easy. So I take my graph, here is PK. I take my graph partition set of the partition, my small pk, and then I say that RH1 is in one side of the one side of the set S1 that I'm interested in, and the other one is in another one. Right? So, and I fix those, and then because I have T of such a different couples, and then I have to check what happens, which one is the minimum of all, because I'm looking for the minimum, looking for the lower bound. So in a sense, I see that 1 and 2 is my probably edge. And I say, okay, if this is my edge, I put one vertex in a set 1, second vertex in a set 2, and then I solve this, right? And this gives me a bound. But this bound does not have to be the valid bound, so I have to check for all combinations and then find the smallest one. Okay, but again, this sounds funny, actually difficult if T is large. So you want to take a look probably later at the graphs that are largest, that have a large automorphism.
But isn't it kind of obvious that you just have to, well, I mean, you have the symmetries, so you just solve your problem up to different possible pairs?
Yeah, this is obvious, yeah.
So don't call it a theorem.
No, but this is this is actually more as an observation, but then nevertheless you have to prove it, right? Okay, so now for each H, I want to compute my graph partitioning vector lifting relaxation with no negativities, and actually this means fixing one set of the vertices of the edges or non-edges, which means adding just this type of the constraints. Okay, so it means I add two types of the constraints and resolve. Okay, so now I call my mu fix is going to be the relaxation which is obtained from the minimum of all these fixings, right? So I have to solve the subproblems. Okay, so let me give you a few remarks about the new bound. It's somehow clear I had extra constraints, so I'm going to improve my bound. So I know that my mu fix is larger than the previous one, which is larger than the eigenvalue bound, is also rather trivial to show. What is my remark is rather difficult to solve this new H for n larger than 55, because then it gets too complicated to solve. But if we try to exploit the symmetry, it means if I try to look at the graphs which have a nice structure, then I can solve to size 216. That's at least how much I try, but I guess it can be better. Okay, so let me show you now a couple of so maybe I should say where I'm exploring the symmetry. So I'm actually trying to explore symmetry from this adjacent matrix A, right? This is similar to what I explained to the matrix lifting approach, but here gets a little bit more involved, so I decided not to talk about this at this time framework. Okay, let me show now the numerical results for the bandits. I'm again going to take a look at the nice group of the graphs. I'm looking at the Johnson graphs. And for the Johnson graphs, you probably know it is let omega be, if omega is a set of the size V, and D is a given number, then my vertices of the Johnson graphs are all subsets of a size D, all subsets of omega of the size D, and we say that two subsets are adjacent if their intersection is D minus 1. Okay, so now some numerical results. So I take different V's. Different V's the size of my set omega, and then I take here D is equal to 3, so I'm looking for all those subsets which are adjacent because the distance is 2. Okay, so these are the number of the vertices in the graph. This is the eigenvalue relaxation which you get. This is the one which you get when you solve just the matrix lifting relaxation, and the new one gives you the same, but this is an upper bound is 22, so actually we have the optimal labeling. And then we go on, and whenever you can actually see that by just doing this simple fixing, you can improve a bound from 69 to 74, which is quite large in this, if you take a look in this framework. But on the other hand, what is also interesting to see for me, because I'm interested also in eigenvalue relaxations, is that eigenvalue relaxation does not get always too bad. It's not always too bad with respect to the also matrix lifting one. Okay, so what did actually we do here? We use our expression, we compute the bound. This is my new fix, and I put it here, and then I compute what is the size of the bound. As far as the upper bounds, so what do we do with the upper bounds? We improve the reverse Cuthill-McKee algorithm. So if you ask me why did you try to improve the Cuthill-McKee algorithm, there is a simple answer. So Cuthill-McKee algorithm, reverse Cuthill-McKee algorithm is very nice algorithm, gives you quite good bound, is very well known. But the problem with this algorithm is, with this heuristic, is that actually it tries always to find the vertex with the smallest degree and then builds up the labeling of the graph. But for me, if you take a look, I have a Johnson graph. The Johnson graphs, they all have the same degree. So it means that whatever I choose, I will not end up too far. So what we improved, actually, try to solve the reverse Cuthill-McKee algorithm and then try to, by the brute force, push some of the vertices inside. And so we get this. So if you compute with the Cuthill-McKee, here will be upper bound about 130, but we get 92. Okay.
Sorry?
So, yes.
So when you say for a certain amount of time, like, what algorithm do you use to solve the relaxation?
Sorry?
What algorithm do you use to solve the relaxation?
This time is quite fast. This is about half an hour to get. So in this half an hour, I'm including solving all three subproblems. And yeah, so it's not very bad. So what do I use? I use I think it says DPT3. But why it gets so nice, because this Johnson graph is a nice Johnson scheme. I have only 3 basis matrices over there, and then it goes very fast. So if I would try to solve this size of the problem without using the symmetry, there will be no computer which can do it for you. So I would probably have to stop at this point, 35, if I want to solve them all. Yeah? Okay. So now let's take a look at the Hamming graph. For the Hamming graph, is a Cartesian product of D copies of the complete graph, right? That's what you all know. Now again, I take a look at the nodes, and again, improvements are rather significant. And again, we used our improved Cuthill-McKee algorithm and so on. So the time is again not too bad for size 216. This is actually about half an hour, right? Yeah, this is about half an hour, 216. Yes, this is half an hour to get the bound. Okay, so we also compute the bounds for some other nice graph groups, for other nice classes of the graphs. And we obtain always the best lower bounds, and we also obtain the best upper bounds. It's interesting, our upper bounds are better than the non-theoretical upper bounds for those graphs. I have a simple answer for this because, for instance, Harper has upper bounds for the Hamming graphs, but they are in general one for any D and any K. But if you actually look for the different fixed D, and then you can get something better than what Harper gets. Okay. So this is one of my last slides, and now I say when you think that it cannot get better, there is still hope that it can get better, right? So still one fish can go to another side. And actually, how this can go better, I can further strengthen my vector lifting relaxation by adding the RLT cut. But due to restriction of my time, I will just do it on some other occasion. We actually did this, and then the bounds even get better. So it is the highest hierarchy. So it went to the hierarchy of size 3, I think, arterial lifting.
What are RLT cuts?
Reformalization, realization technique. So this is what Sherrill and Adams were doing. So you know what they were doing. They just make a combination and then introduce one variable to linearize. So you can actually add a RLT cut to the QAP, and then you can go to size 3 or 4 level of hierarchy. I think level 3 is somewhere highest one that currently we can do. Okay, so but I'm going to talk on some other occasion, and thank you very much.
Some questions?
So in that bandwidth computations, do you, I mean, in the last part, did you use symmetries of your graphs?
Oh yeah, sure.
So you basically reduced the dimensions of your ZPs?
Yes.
They were not really at 165, but only
Yeah, but
small?
yeah, they were small. But you see, I am now fixing the two edges, the two vertices.
Right.
So I'm looking at the
still the
stabilizer
right? So
over the
it's-
set, and then it gets sometimes gets bad, right? Because you don't know how it looks like. So I'm using the gap to find from the stabilizer by fixing two vertices, and then it's not so nice as if I would just do it by solving the original one. But if you see the times, it actually here. So if I just solve the standard one, without fixing, I just get it in a few seconds, 35 seconds. But here the time increases because number of the basis matrices for the stabilizer are not always so small. Right?
Actually, my question is about your first part, about the GPP closed for the relaxation, that you relax the diagonal constraint being all ones to the trace being A.
Yeah.
It's
Being N, yeah.
yeah. And so, for example, if what I think is that you have N hyperplanes, and then now you use one hyperplane
Yeah.
to reduce. What is the when you relax that from N hyperplane to just one hyperplane?
Yeah.
What is the gap? What
Yeah,
is
the answer
what
is-
the case in your analysis. Why you? Yes.
So the answer is rather simple because I have this Laplacian algebra, and I want to use the properties of my Laplacian algebra, and this is the best what I can do in this moment because I know what are the traces of those basis matrices in my Laplacian algebra, so that's what I'm using. And if I would not relax that one, then I would not be able to use that properties, and then I would have a linear combination of the diagonals of those matrices, of basis matrices from the Laplacian algebra, for which I don't know what is. But the nice thing is actually what I do, what I think here is that I'm not interested in how those matrices actually look like, right? I don't want to compute them, I don't want to have anything with them. I only use the property what is their diagonal, yeah? And a trace, what is their trace, sorry. And this is the only thing, so I don't need them at all.
But this is strange because your matrices they come from the periodic products of eigenspaces.
Yeah.
So if your eigenvectors are normalized, then you should have constants on the diagonal.
But no, those are not right. These are so if you take you.
Okay, so you because you are not full range, so you also get zeros.
Yes,
or-
I'm not the full range. That's a problem because these are just each column of this UI is just all orthonormal vector corresponding to the eigenspace of lambda I, right? So I can have only one there. I can have two, depending on the multiplicity, right? So yeah, right. I have zero somewhere, but there does not have to have a constant diagonal in general. For some nicer graphs, I can find those with a constant diagonal, and then probably I will end up with the same what I had for the strong regular graphs, I think, right?
So for this part, if the graph is vertex sensitive, then like this, there's no difference. I mean, it should not change the relaxation, right?
No, I don't change. I don't care if it's a vertex transitive.
But no, I meant that like this where you replace the constraint on the diagonal to a constraint on the trace.
Yes.
Like that's equivalent if it doesn't change anything if the graph is vertex sensitive.
Yeah, if the graph is vertex transitive, I would then have only one orbitals, right? So the diagonal will be the constant. Yeah, in that sense.
See, but the vertex sensitive is a large symmetry.
Yeah. Yeah, because I end up with one orbital. Sense. Yes.
I remember for the low Bash theta function of the graph, it doesn't make any difference. The bound is the same. You get the theta bound regardless of whether you use the trace version or whether you use the diagonal version, which is quite surprising.
Yeah, this is really surprising,
There
right?
are two different, well, there are several different ways of getting a theta bound, and one of them you just say the trace is 1, and then the other one you constrain every element of the diagonal and give you the same bound.
But you have some extra constraints or not? I think there is
Yeah,
something
yes.
extra there.
Oh,
Yeah?
yes.
Yeah, there is something extra, but I don't get everything extra. The problem is, this actually are coming for where I want to come in the next few months or next few weeks, because I know what I do. It's now right, really quick and dirty, right? But I want to somehow improve it. So probably you're leading me to the right way to look at those papers and see what I can eventually add, so that I replace this constraint with that one. Yeah. I mean, I need to add something more. I also removed the non-negativities here.
But if you could calculate those bounds in 1 or 2 seconds, suppose I tell you how to do that.
Which ones?
We're 1600 seconds. I tell you a way to do it in 1 or 2 seconds.
Okay.
I don't know it, but
Yeah.
suppose I could. So
Yeah.
then you really get excited, start thinking about maybe
Yes.
globally solving by branch and bound. But somehow you have to branch in a way to preserve symmetry, otherwise
Then it's gone. Yeah.
yeah. So have you thought about if there's a reasonable way to do that, to keep the symmetry as you go?
Yeah, this is also one of the ongoing things. So we still don't understand what happens, because you see here already it gets bad, right? Because if I solve the Ruth node, oops, sorry. So if I would solve the Ruth node, then I would get it maybe in 35 seconds for size 165. But then if I fix one vertex, then it gets a little bit worse. If I fix two vertices, it's nothing else but just going down to the level of branching tree, right? So just fixing two vertices, checking the all options. So it would get worse. I actually tried to fix the triangles, but I just could not solve it anymore because it gets too many basis matrices, so it just was not useful. But for some graphs, maybe I can fix the triangles. I was actually thinking to do that. But further than triangles,
So
I
something
doubt.
clever based on the orbitals, or
no, not that I know. No, not that I'm aware. Maybe Dima knows.
Exactly.
maybe we should talk offline. So.
There was a paper, wasn't there, just a couple of years ago called orbital branching?
Yes,
Yeah.
but that's for the integer programming.
Yes, it is, yeah. I just wondered
Yeah.
whether you can use a similar branching strategy.
Yeah, it gets a little bit difficult because you have really matrices here. I think it gets difficult, but actually the idea would be to solve this for the larger sizes, this one using the symmetry. So far you can go, and then it would be nice here to have a matrix lifting for this, but this is a rather difficult matrix lifting for the min cut.
Okay, let's thank Renata again.